Today I want to start talking about some modern physics, and this is one of my favorite things to talk about. Thus far in this class, semesters 1 and 2, we've been mostly talking about physics from the 1600s, the very end of the 1600s, the 1700s, and the 1800s. The 1600s saw Newton's famous publications, Newton's laws of motion, that kind of thing. In the 1700s, we saw the development of theories of energy. In the 1800s, we saw electricity and magnetism come to its full fruition. Also, a modern theory of heat was developed in the 1800s. The electron was discovered in 1897. The proton followed a few years later, and the neutron a few years after that. So the atomic theory was coming into fruition around the turn of the century, and that's pretty much where we've stopped our journey thus far. In these last few sections of the book, we're going to move forward into some 20th century physics. And I just love talking about this stuff. We've all had however many years on this earth. I've had 43 years on this earth to develop some sort of a common sense notion of how this world that we live in works. And if I toss this eraser, it's just going to do that, and nobody's surprised. It totally jives with my common sense. I could ask you a physics problem that was fairly challenging on it, but it wouldn't blow your mind, right? We talked a little bit about magnets. Magnets can be surprising, right? Magnets can be real surprising a little bit. This repulsive action, this action at a distance, the long-range force. That's a little bit surprising when you really start thinking about it. But again, it's not making our brains bend too much. But when we start talking about relativity and quantum mechanics, which are the next two big topics, then we're going to find that your common sense goes this way, and logic will force you to go this way. And I just love that. So we're just going to dive in here, and we're going to start talking about relativity. So here we see a picture of Einstein, the man who came up with a modern theory of relativity. So here we see Einstein as an older man. This is probably the image you have in your mind of Einstein. Here he is as a younger man in his 20s. This is taken probably right around the time that he made some of the famous discoveries that we're going to be talking about in this class. Einstein was born in 1879 in Germany, and he worked his way up, and he was working on a PhD in physics, and he was supporting himself at the time by working in the Swiss Patent Office. And he did have a scientific type job. He was reviewing patent applications for their scientific legitimacy. And so that's where he was working when he made these discoveries that we're going to be talking about here today. This was in 1905. That same year, he came up with the special theory of relativity, which we're going to talk about here. He also came up with a solution to something called the photoelectric effect, which we're going to dig into in the next chapter. He actually won the Nobel Prize, not for relativity, which is what he's the most famous for. He won the Nobel Prize for his solution to the photoelectric effect problem, which we'll talk about in the next chapter. He also came up with this idea of Brownian motion, and this led to the atomic theory, or it was in support of, I should say, the new atomic theory. This is the idea that if you look at a tiny, tiny dust particle, a so-called dust mote, then a tiny dust particle will seem to move around randomly. And really, nobody knew why. And so Einstein came up with this idea, something we've talked about in other parts of this class, that maybe that little dust particle was moving around kind of randomly because of collisions with something that is so small we can't see it. Maybe there's atoms or molecules that are moving around very quickly and having collisions with that dust particle. He also published his most famous contribution, possibly, the E equals mc squared paper, the equivalence of mass and energy. That's something we'll also get to talk about in this chapter. All of those papers, and he got his PhD in the same year. I've never had a year like that. Okay, we're going to talk then about relativity. So that was in 1905. In 1916, he published his other really, really famous paper on general relativity. That's something that we'll just mention in this section, but the mathematics of that is very challenging, and we're not going to get into that at all, beyond mentioning a few of its consequences. So in 1933, he actually was visiting the United States, and Hitler came to power while he was in the United States. Einstein decided to stay in the United States. He finished out his career at the Center for Advanced Studies in Princeton, New Jersey. So, in order to kind of wrap our brain around how profound Einstein's idea of relativity is, we need to back up a little bit. And we need to think about some things that are sort of implied assumptions about what we've been learning about so far. Some implied assumptions in the content that we've been learning about so far. And so, in Newtonian mechanics, we assume that space and time are absolute quantities. I'll go into that just a bit more in just a second. But in the modern theory of relativity, lengths and time intervals depend on the motion of the observer. And so, let me show you what I mean by that. To help us wrap our brain around this, let's take a specific situation and compare how they might look according to what we've learned so far and according to this new theory of relativity that we're going to dig into here. So what do I mean by space and time are absolute quantities? Well, here we have a situation here, and I am in my super fast Speedo 5000 rocket ship here, and it is going through space real fast here. And in fact, it's going 90% of the speed of light. Now, we know the speed of light is fast, 90% of the speed of light, that's super fast, right? Humans don't have a spaceship that actually goes that fast, so this is a thought experiment. And meanwhile, I'm here and my buddy is down here hanging out on Earth. So this guy's hanging out on Earth and I'm flying by at 90% of the speed of light. I'm sitting here and I'm inside my rocket ship and I'm watching a lovely cat video on YouTube. It's hilarious. And it is 3 minutes long. It is a 3-minute long cat video. And I am flying by in my Speedo 5000 spaceship. And it turns out that on the showroom floor, the length of this is 100 meters. Okay, so according to everything we've learned so far, and I'm guessing, I'm not in your brain, but I'm guessing according to your common sense, my friend on Earth and myself in the spaceship both agree on two basic facts. That is, that my cat video is 3 minutes long and that my spaceship is 100 meters long. According to everything we've learned so far, that's the end of the story. But according to relativity, it is not the end of the story. According to relativity, actually, I observe my cat video to be 3 minutes long, but according to my friend on Earth, it is 7 minutes long. It's almost 7 minutes long. And you might say, well, how can that be? Who's right? The answer is they're both right. And it's super weird. I think this one's even maybe a little bit weirder. It turns out that we don't agree on how long my spaceship is. According to me, who's traveling with the spaceship, my spaceship is 100 meters long. That's how long it is on the showroom floor. But guess what? According to my friend who is on Earth, this spaceship is only about 44 meters long. Who's right? It's the same spaceship. How can it be 100 meters long and 44 meters long? That's what I mean about not jiving with your common sense. They're both right. It depends on your relative motion. Ground-based observers measure the length of a fast-moving rocket to be shorter and a clock on the rocket to run slower compared to a rocket that is at rest. So I've used the cat video as a proxy for the clock. It runs slower. It takes 7 minutes for the cat video to finish according to observer on Earth, and only 3 minutes according to an observer on the spaceship. It's pretty weird. We're going to spend a while talking about this. This is just an introduction to let you know kind of where we're headed and to hopefully encourage you to keep your mind open and look out for those places where your common sense is actually wrong. Okay, so special relativity deals exclusively with inertial reference frames. And we're going to go into that a bit more here in a second. But in inertial reference frames are reference frames that move relative to each other with a constant velocity. What is a reference frame? Well, It's basically a set of axes and a clock. We'll talk just a bit more about what that means in a second. Now, general relativity is a more encompassing theory that considers accelerated motion and its connection to gravity. So the special theory of relativity Einstein published in 1905, and then he followed up with it with general relativity in 1916. A reference frame is a coordinate system in which experimenters equipped with meter sticks, stopwatches, or any other equipment can make position and time measurements on objects. Okay. So we've actually been dealing with reference frames all along. I just really haven't used that terminology. So there's some ideas here that are implicit in the idea of a reference frame. A reference frame extends infinitely far in all directions. So when I talked about this example here, I'm talking about two different reference frames. There's the reference frame of the person on Earth, and there's the reference frame of the person in the spaceship. And these overlap, and they extend infinitely in all directions. The experimenters are at rest within their reference frame. According to this guy, he is at rest on the Earth, and I'm just sitting here watching my cat video, right? I don't have a sensation of flying through space. I'm just sitting there watching my cat video. And you might say, Foxley, you're pulling a fast one on us. We know that this guy's really moving. I don't know. I don't know about that. Are you moving right now? Do you feel like you're moving? My guess is you're sitting in your living room somewhere, I don't know, your bedroom, and I'm guessing you don't feel like you're flying through space. But guess what? You are, right? The Earth is rotating on its axis. The surface of the Earth, where we are, is rotating. We're moving about 700 miles an hour relative to the center of the Earth. So I've been, lecturing for what, 15 minutes or something on this video. This video's, according to our reference frame, we're about 15 minutes into this video. So since you started watching this video, you've moved something like, almost 200 miles. Did you feel like it? No. Why? Because you're at rest within your reference frame. That's what the second bullet is talking about right here. And further, the number of experimenters and the quality of their equipment are sufficient to measure positions and velocities to any level of accuracy needed. And so the point here is that we're mostly dealing with thought experiments here, right? So we can say, well, how would I manage to measure this as he's flying by? How would I even do that? Well, I don't know. I'm not saying it would be easy to do, but we're just imagining that whatever it takes, this guy's got it. So that's what we mean there. And I just want to point out that this is not this bizarre situation where we're measuring two different lengths for one object. This isn't because one of these guys is bad at measuring, right? Or one of them made a mistake. No, they both, again, that's what this last bullet point is about. Both of these, we trust both of these measurements, right? We will label our reference frames with an S. And so we say S and S prime are two different reference frames. We have the S reference frame, which we will say is at rest, and we have the S prime reference frame, which we will say is the moving reference frame. Now, these reference frames could be moving in any direction relative to each other. In this conversation, in this chapter, we're going to constrain the motion to the x direction. So we're talking about motion in one dimension. We might as well make it in the x direction. So we see that all of the motion of these two reference frames relative to each other is along the x-axis. And we say the origins coincide at t equals 0. And so at t equals 0, S prime and S are in the exact same place. They are overlapping and basically the same reference frame. As time moves on, S prime moves away from S. They're moving relative to each other. It's important that we talk about an inertial reference frame because special relativity is all about inertial reference frames. And an inertial reference frame is essentially a non-accelerating reference frame. And so, to be real specific though, we're going to go ahead and say that A equals 0 when F equals 0. That's what an inertial reference frame means. And to tell you, to give an example here, we see this airplane right here. This airplane is flying at a constant speed or is at rest on the ground. Either way, if I don't put a force on the ball does not accelerate. It sits there at my feet. However, if you imagine doing the same experiment in an accelerating airplane, then I would stand there, the plane accelerates, and I would see the ball head to the back of the airplane. In other words, the ball would accelerate, but nobody pushed on it. Therefore, it's not an inertial reference frame. This is a technical definition, and it works great, and it's not too abstract, but you know what? An inertial reference frame is a reference frame moving at a constant velocity. That's a little bit more intuitive, and we can roll with that. So we can do relativity in Newtonian mechanics, sort of the non-Einstein version of relativity, and all we mean is, you know, if I know your velocity in one reference frame, well then what is your velocity in another reference frame? And so we would call that the Galilean principle of relativity. What is that? Well, it's that Newton's laws of motion are valid in all inertial reference frames. So this is the Galilean principle of relativity. Basically it says, if I discover the laws of physics in my reference frame, and then I go to another reference frame, then I should discover the same laws of physics. So some notes here. Any reference frame that moves at constant velocity with respect to an inertial reference frame is itself an inertial reference frame. Again, an inertial reference frame is just a reference frame that moves at constant velocity. And any reference frame that accelerates is not an inertial reference frame. Let's do a quick clicker question. What is an inertial reference frame, or at least a very good approximation of one? Why don't you pause the video and give it some thought? I'll see you on the other side. Well, let's see. A jet plane during takeoff. I think that's accelerating. So I don't think A is an inertial reference frame. A jet plane flying straight and level at a constant speed. That is. I would say that is not accelerating. I'd call that a pretty close approximation of a inertial reference frame. How about a jet plane turning at a constant speed? Well, if a jet plane is turning, it is accelerating, and therefore that is not an inertial reference frame. So I think the best answer is B, a jet plane flying straight and level at a constant speed. That's what an inertial reference frame is. And let's be clear, it's not that we couldn't do relativity in one of these situations. It's just that we would need general relativity, where the math gets a little bit weird. In order to understand how strange and surprising Einstein's theory of relativity is, we need to have a reference. We need to slow down, and we need to spend a little bit of time talking about Galilean velocity transformations. In other words, we need to spend a little bit of time talking about how velocities look in a Newtonian perspective, because only then will we be able to appreciate how strange velocities look in a Einsteinian perspective. These guys are all near or on the same road. Sue is standing beside the highway as Jim drives by at 50 miles per hour. Jim and Sue will measure the motorcycle moving at different speeds. The point here is that, according to Sue, she sees the motorcycle moving away from her at 75 miles per hour. But what does Jim see? Does Jim observe the motorcyclist moving away from him at 75 miles per hour? No, he doesn't. Doesn't Jim observe the motorcycle approaching him at 25 miles per hour? That is a Galilean velocity transformation. And again, I think it just jives with your common sense. If you're thinking, yeah, well then, yeah, I agree, right? It's fairly straightforward. This is the Galilean transformation. So an object's velocity measured in frame S is related to its velocity moved in frame S prime by V's equation. Prime always refers to a quantity in our moving reference frame, and the unprimed quantities are in the unmoving reference frame. And we have to be a little bit careful. We're using V for the velocity of the reference frame, and so now we need to use U for the velocity of some object within that reference frame. So let's see if we can't use these equations to get the answer we were expecting out of this. In other words, we want to know, what is the velocity of the motorcycle as measured by Jim? Well, let's write down the different quantities, and I think we'll see that we do come up with 25. Okay, so what are our quantities? Well, in this case, v is the velocity of the reference frame. And since we're asking according to Jim, well, Jim is an experimenter within Jim's reference frame, within the S prime reference frame. So that means that v is 50 miles per hour. That is how fast the S prime reference frame is moving with respect to the S reference frame. U is the velocity as measured in the S reference frame. The velocity of what? The velocity of the motorcycle, because that's what we're interested in. The velocity of the motorcycle in the reference frame at rest, in the unprimed reference frame, is 75 miles per hour. U prime, that is what we are looking for. That is our unknown value. So, going now to these transformations, we have U prime equals U minus V, and that is going to then be 75 minus 50 equals 25 miles per hour. Okay, again, not terribly surprising. Again, if Jim looked in his rearview mirror, he would observe the motorcycle coming up behind him at 25 miles per hour. That's what we mean by this. That is a Galilean velocity transformation. Let's do another example. So these transformations, they should work for an object, like a motorcycle, but according to everything we've learned so far, they should also work for waves, like, say, a sound wave. So here's an example, and again, we're just really doing physics 1 here, but we're trying to just establish some things solidly so that when we move on and see how these things look in relativity, you can be appropriately surprised. An airplane is flying at a speed of 200 meters per second with respect to the ground, okay? Sound wave 1 is approaching the plane from the front. Sound wave 2 is approaching the plane from the back. Both waves travel at 340 meters per second relative to the ground. What is the velocity of each wave relative to the plane? Okay, well, let's just make a few, let's list our variables here. So, what are our reference frames here? Well, the S reference frame is attached to the ground. So the S reference frame is unmoving, and it is attached to the ground, because we've got all these numbers with respect to the ground. So all of these numbers are all with respect to the ground. And we're trying to figure out, so we know the velocity of the waves in the S reference frame. We're interested in finding the velocity of the waves in the S prime reference frame according to the spaceship. So our S prime reference frame then must be attached to the spaceship. So now we are ready to list our variables. Well, how fast is the reference frame moving? That's V. V equals 200 meters per second. And then we have U of sound wave 2 is equal to positive 340 meters per second. U1 is a tiny bit tricky. It's headed in that direction, so that's negative 340 meters per second. Let's do our Galilean velocity transformation. We know that U prime equals U minus V. So let's write that. So that means that u prime 1 equals u1 minus v. u1 is negative 340 meters per second minus 200 meters per second. Negative 540 meters per second. Whereas u prime 2 equals 340 meters per second minus 200 meters per second. Equals 140 meters per second. Okay, do these numbers make sense? Well, I think so. You know, this one is kind of chasing it, right? And so it makes sense that, you know, if this guy looks in his rearview mirror, he sees this approaching at 140 meters per second. However, if he looks out his front windshield, he sees this wave approaching at 540 meters per second. Because according to this guy in the spaceship, he's at rest, right? According to himself, he's at rest in his reference frame. And he sees the sound wave heading in that direction. That's why it's negative at 540 meters per second. He sees this sound wave heading in that direction. That's why it's positive at 140 meters per second. Again, this really is physics 1. Hopefully it's not too surprising. Okay, so we've talked about this a little bit. Let's you try one now. Race car driver Sam is headed down the final straightaway, approaching the finish line at 100 meters per second. His fans at the finish line straight ahead are shouting. The speed of sound on this hot day is 350 meters per second. How fast are the sound waves of the shouts approaching in Sam's reference frame? Is it 100 meters per second, 250 meters per second, 350 meters per second, or 450 meters per second? Or is this just a big joke? Why don't you pause the video and figure it out? Okay, so here I've drawn the situation. Got Sam driving in his race car. Here are his fans. What are these values? Well, we know how fast the sound is moving according to the fans who are at rest. We want to know how fast it's moving according to Sam, who is moving. Therefore, the S prime reference frame is attached to Sam. And the S reference frame is attached to the fans. So, that makes V 100 meters per second. It makes U negative 350 meters per second. U prime is U minus V negative 450 meters per second. Okay. So, hopefully you agreed. Notice the velocity is negative 450 meters per second. I said how fast. How fast is not a vector, so that's why I don't have a negative sign here. Okay, so 450 meters per second. Not too bad. And if you didn't have to do all this, if you didn't have to write it all out here, that's just fine. We're just trying to wrap our brains around what's going on here. So now we've kind of gotten caught up a little bit on Physics 1 and how these velocities add for waves or for motorcycles according to Physics 1. Let's think about how that looks like in relativity. I think you might be surprised. Okay, so again, we need to back up just a little bit. Prior to Einstein, it was hypothesized that space was filled with something called an ether. Now, if you'll recall from last semester when we first learned about waves, we learned about mechanical waves and non-mechanical waves. Mechanical waves require a medium to travel through. For example, sound waves. Sound waves won't travel in space. Sound waves are a mechanical wave, and in space they don't travel. Right now I'm speaking, and they are traveling through the air and being picked up by the microphone on my computer. A water wave, obviously, needs a medium, the water, in order to go somewhere. Light was tricky. Light was really tricky. In the 1800s, Maxwell and others came up with this theory of electromagnetic radiation, which we've learned about, wherein we treat light as a wave. And it's a great description, right? we can describe all sorts of phenomena by treating light as a wave. But then the question is, what is the medium that the wave travels through? And so, for a long time, it was hypothesized that the light was traveling through something called the ether. It was this medium that filled space, and somehow it didn't slow down our Earth as we were going around the sun. There's no viscosity or friction from it, but yet it was able to carry these waves. This is the theory. Which means that all this math that we've just been doing should work for light. And so, in other words, the velocity of light that we measured should depend on how fast we are moving with respect to the ether. Kind of like in this last race car example that we did, the air is carrying the sound wave. So the velocity we measure for the speed of that sound wave depends on whether or not we are moving with respect to that air, as we've seen in the previous couple of examples. So folks were trying to do experiments, trying to figure out whether this is true. And one kind of clever idea that some people had for measuring the speed of the ether, or the Earth's speed through the ether, how fast the Earth was moving through this ether, is you take some very, very distant star out here. And of course this star is shining light in all directions. And then we take, here's the sun, okay? And of course the Earth is orbiting around the sun. And the Earth is moving very fast. It's not moving at the speed of light around the sun, but it's moving pretty dang fast around the sun. And so, and let's say that this is in the spring here. We've got a very large velocity in this direction, and let's say this is in the fall, and I have a very large velocity in that direction now. So, if this theory of the ether is correct, then we should be able to measure the speed that this light is being emitted, we should be able to measure the speed at which the light arrives at the Earth. We should measure something different in the spring than we do in the fall. Thinking back to our race car examples, right? If Sam suddenly slammed on his brakes and turned around and raced the other direction, then he would measure a different value for the speed of those sound waves approaching him. Just like here, we should measure a different value for the speed of light approaching. But guess what? They didn't. And so people got real good at measuring this, and they found they got the same value here as they did here, which was really puzzling. That was really, really puzzling to people. And so in the 1800s, again, like I'd said, this theory of electromagnetic radiation had been pretty well developed. And this theory predicted that light should travel at 3 times 10 to the 8th meters per second. Notice these are our good friends. The permittivity of free space and the permeability of free space are electric and magnetic constants. And interestingly, and somewhat surprisingly, they have a very deep connection to the speed of light. And so it was thought that this was really the speed with respect to the ether. But people are doing these experiments, and they're finding that the value is constant no matter how fast the observer is moving. Very surprising. Most scientists at the time sort of chalked it up to experimental error. It just didn't make sense that you should measure the same value here as here. It didn't jive with anybody's common sense. But Einstein had this ability to think outside the box, to use a colloquialism. I call it creativity. I really think that science is fundamentally a creative endeavor. And Einstein was an unbelievably creative man. And he said, hey, you know what? As weird as it is, maybe that's just how the world works. And so Einstein hypothesized that all the laws of physics, not just Newton's laws of mechanics, hold in any inertial reference frame. So, principle of relativity is this is Einstein's principle of relativity. And it might seem straightforward. We're going to see that it has some surprising conclusions. All the laws of physics are the same in all inertial reference frames. which means that if Maxwell's equations predict this value, 3 times 10 to the 8th meters per second, for the speed of light in the ether, then light should travel at that speed in all inertial reference frames, and we don't even need the ether. We can just get rid of this idea of the ether. This is just how fast light travels, according to all observers. This isn't surprising unless you've really wrapped your brain around the way those sound waves work, right? Not every person measures the same value for the speed of those sound waves. Yet, Einstein's saying everybody will measure the same value for the speed of these light waves. Now, I want to be real clear about this. This is the principle of relativity, that all the laws of physics are the same in any inertial reference frame. In other words, if I discover the laws of physics here on Earth, and some other species on another planet far across the galaxy discovers the laws of physics, then we should agree even if we're moving at different speeds on different planets. It seems reasonable. That really is the principle of relativity. Some people think the principle of relativity is, E equals mc squared, or you can never go faster than speed of light, or cat videos aren't the same length in different reference frames. Spaceships are different lengths in different reference frames. Those are consequences of the principle of relativity. So what we're going to see is we're going to say, okay, let's start with this assumption. What else is true? Let's find out. There's some surprising conclusions.